CMA, a chromaticity map adapter for robust detection of screen-recaptured document images. Our research focuses on document image detection technology, which is becoming increasingly important in modern e-commerce and e-government. As more documents such as IDs, contracts, and certificates are digitized, the security and integrity of document information face unprecedented challenges. While digitization brings convenience, it also introduces potential security risks. This is particularly critical when confidential documents are handled by government departments and commercial companies. For instance, during the COVID-19 pandemic, a Samsung employee leaked business secrets by photographing internal documents and sharing them. Our system inputs document images and outputs classifications of the images as genuine or recaptured based on forensic features. Applications of this technology include enhancing document security, aiding digitization processes, and preventing unauthorized dissemination. Many existing methods face certain limitations. Firstly, unlike face detection technology, document image detection encounters unique challenges. Face images often contain rich 3D depth information, aiding in feature learning and recognition. However, document images are typically planar, lacking depth information, which limits the direct application of many depth-based face recapture detection techniques in our context. Additionally, many detection techniques for natural images, such as those detecting LCD screen recaptures, focus on analyzing global image features like moiré patterns. These techniques are less effective for document images because recaptured documents often undergo compression and resizing when shared via social networks, weakening these global features. Furthermore, our group's previous works have focused on using halftone textures in the printing channel to detect printed recapture documents, but these methods are not directly applicable to lower quality screen recapture samples. Upon closely examining screen recaptured document images, we observed that colored artifacts typically appear around the text edges, a phenomenon not present in printed samples, highlighting its potential as a distinguishing feature. More importantly, these colored artifacts demonstrate robustness in low-quality samples, providing an effective detection means. Based on this discovery, we proposed a new method using a chromaticity map adapter (CMA), which inputs chromatic information as visual prompts into the network. Our adapter effectively converts this information into a format that the network can understand and process. This structure allows the network to learn basic texture features of the images, while also learning and utilizing chromatic information left by the color artifacts generated during the screen recapture process. To better understand the origins of the color artifacts in screen recaptured images, we proposed a theoretical distortion model based on the actual physical process of screen recapture. This model focuses on the signal distortions occurring during the screen display and camera recapture of document images. To validate our theoretical model, we used one-dimensional signal simulation and image simulation methods, proving the reasonableness and practicality of our theoretical distortion model. Firstly, we simulated the intensity output of each color subpixel on the screen through an ideal spatial light modulation process. Each subpixel's intensity can be viewed as a rectangular function, reflecting the spatial distribution of brightness for each color channel in the physical domain of display devices. We then described how these rectangular functions synthesize the color content of a pixel on the display. This process considers the independent operation of each color subpixel, combining the intensities of the red, green, and blue channels in parallel to form the final pixel color. The detailed process of how screen content is captured and converted into a recaptured image involves two key steps: blurring and resampling. Blurring is due to the low-pass filtering characteristics of the camera imaging system. Resampling involves the camera sensor sampling the screen content at certain spatial intervals, which can lead to color artifacts in the recaptured image. Extracting chromaticity maps is a crucial step in understanding and utilizing the color artifacts. This process captures the imbalance in the RGB color channels of the input image, emphasizing this imbalance through normalization, thereby highlighting the color artifacts in recaptured images. Chromaticity maps are calculated by determining the deviation of each pixel's RGB value from the average value of the other color channels. The core design of the CMA is to convert chromatic maps into a form directly usable by deep learning models, enabling efficient detection of screen-recaptured document images. The CMA network captures the chromatic features of the image and converts these features into visual prompts, which are then input into a transformer backbone network to enhance the model's ability to learn and recognize recaptured image features. To effectively evaluate the performance of our network, we constructed and shared a dataset named ROD, containing 10,887 genuine and screen-recaptured document images. The dataset includes three subsets: high-quality, headquarter, low-quality, LQ, and mixed-quality, M and F, images. These subsets ensure the diversity and practicality of the dataset by simulating various real-world challenges. Our extensive experiments show that the CMA network significantly outperforms single-modal RGB-based methods, especially in low-quality images, confirming the effectiveness of leveraging chromatic maps and multimodal learning. Robustness tests demonstrate the network's high adaptability to common distortions, such as compression and resolution reduction, emphasizing the practical applicability and effectiveness of CMA in real-world conditions. Overall, the CMA network shows strong performance and reliability across diverse scenarios, proving the potential of chromaticity maps in handling complex and varied situations in document image detection.